How y'all doing? Any questions, thoughts, concerns, etc. before we get started today? All right. So, over the last week, we've been looking at Newton's laws and different types of force. Today we're going to try to tie all those things together into one more big example. Before that, just to quickly summarize the last week or so, we got Newton's laws themselves. Law 1 is the law of inertia. It says that matter is lazy and it wants to keep doing whatever it is it's already doing. Law 2 is net force equals mass times acceleration. Very useful formula. Law number 3, for every action force, there is an equal and opposite reaction force. Using these laws, we have examined at least 4 different forces, those being gravitational force, which is just weight, normal force, which is when you press into a surface, it reacts by pressing back out of itself, usually to hold you up and keep you from falling through it. Tension, which is the force that ropes exert, namely inward on both sides. That'll be relevant today. And lastly, friction, force created whenever matter tries to move through or across other matter. It always opposes motion, so whatever direction motion points, friction points opposite that. And today, we're going to bring all that together in one big example that uses all of them. So, questions or concerns before we get started with one big sample question today? All right. So, and here we have an interesting situation where 2 objects are connected via a string, and that string runs over a pulley. Now, within physics, the main purpose of a pulley is simply to change the direction that a rope is pointing in, usually midway down its length. Here, just to label these box 1 and box 2, the rope begins at box 1, and partway along its length, this pulley changes the direction of the rope from horizontal to vertical. Now, it's still the same rope, and because it's the same rope, it is actually pulling with the same amount of tension on both sides, because all ropes always pull with the same amount of tension on both sides, even though that always means 2 different directions. And here, that also means within 2 different axes, because the purpose of this pulley is to change the axis that the tension is in. When we defined tension, we said ropes always pull inwards on both ends and always with the same amount of force on both ends. So, one of the tricks that we're going to use to eventually solve this particular situation is knowing the fact that whatever that tension is, it is pulling with the same force on both of these objects. The rope is pulling with the same tension on both ends, even though the pulley changes what axis that means. It's still the same rope, the pulley just changes its direction. And that is, once again, the main function of a pulley. More complex pulleys that do additional things also exist, but again, the main function is and has always been changing the direction of tension. As a quick example, let's say that this is a pulley, possibly at, say, a dock or behind the stage at a play. And let's say you're using this pulley to lift a heavy object. You're pulling down with 100 newtons and the box weighs 50 newtons. So that is enough force to lift the box, but the pulley has the benefit of allowing it to get up here, whereas your arms would only get it about here. So we're exerting enough force to lift the box. Box's weight pulls out on this end. The person is applying force down on this end. And what the rope is able to do is it's able to take your downward force here and turn it into upward force on the other end. Now, where the person is, tension actually points also up because again, the pulley has changed the direction of the rope. It's still inward on both ends. The pulley just kind of changes the perspective of what inward means. But it's still inward. You see that? Okay. So, kind of a normal way to think about a pulley. Still inward on both ends, and it's still being pulled outward on both ends. And here we've got the same thing. It's just a 90-degree turn instead of a 180-degree turn. Okay, so far, just as set up. There's one other thing I want to point out about this scenario that will be mirrored in the question we're about to do. And it's that the rope will exert the same tension inward on both sides, but that tension does not necessarily need to be the same as the force being pulled upon it on either end. Just as sample numbers, just to kind of build a frame of reference. Person pulls with 100 newtons, box pulls with 50. That's a different amount of tension a different amount of outward external force on either side. The tension on both sides has to be the same number, but that doesn't mean it's the same number as either of these. In fact, the tension would need to be a different number in order for this to actually work correctly. Because the whole goal of this scenario is to lift the box while you stay on the floor, right? That would be the goal of trying to use the pulley to get the box up. In order for the box to rise, the value of tension does need to be greater than the weight of the box. So T would need to be bigger than this. But on the other side, you don't want tension to be bigger than the force that you are applying, or even your own weight. Because if T was bigger than this, you would rise. And if you want the box to go up, that's not usually how you want that to work. In fact, this system shouldn't cause both objects to rise unless some third other thing was lifting the pulley up higher. So the tension, again, it's the same on both sides, but it needs to be bigger than the box's weight and smaller than the force that you are creating in order to make sure that everything evens out, box rises, and you stay on the floor. So again, the rule is tension is the same number on both sides, even if the pulley changes the direction, and that it is not necessarily the same number as what is being pulled on either side, pulled outward. That is going to factor into what happens here. Is it an okay frame of reference for right now? Okay. So, back to the actual question that we're looking at today. Here we have two objects connected via a string. That string is running over a pulley. And the pulley is just to change the direction of the tension. Both objects are going to have some amount of tension acting upon them, same number for each. And box 2 is just hanging in midair. Box 1 is sitting on the table. And that means that box 1 is going to have some amount of friction acting on it, because it's touching this surface. And friction is going to act to either try to stop box 1 from moving or try to slow it down if it starts moving. So we've got the weight of each box. Box 1 weighs 100 newtons, box 2 weighs 50 newtons. And we have also been informed of the two different coefficients of friction for box 1 sitting on the table. I've written the numbers that we have over here already. Box 1 weighs 100 newtons, and the coefficients of friction between it and the table its static coefficient is 0.49, and its kinetic coefficient is 0.32. Separately, box 2 weighs 50 newtons. And those are all the numbers that the question outright tells us. Any questions about this physical scenario before we look at what we're going to calculate here? Okay? So, that's our physical setup. 2 boxes connected by a string. Now, if you walked into a lab room and you saw this, like I was building this, and I let it go so that it starts doing whatever it is it's naturally going to do, what are the 2 different chains of events that you might expect to happen here? What are the 2 possibilities of what will occur if I build this and then let it go to do whatever it's going to do? Bless you. Sorry, say again?
2 rises or it pulls 1 down.
Okay. Now, if I'm not doing anything extra here, the only reason 2 would rise is if something was pulling backwards on 1, and there's no external forces here to do that. So, correct, there's a way that 2 could rise, but specifically without outside interference, that's not going to happen in this specific case. You are correct, though. It is very likely that 2 could start descending downwards, in which case, via the string, it's going to pull 1 forwards along with it. Now, sorry, did you have a hand up?
Yeah, but never mind.
Okay. Do please ask questions. If you don't know what they are, you can let me know you're confused and we'll try to figure it out. Now, the other option that could happen, especially if the table was very rough, is box 1 just doesn't move. If friction is very powerful, there's a chance that box 1 is just held in place, right? Especially if the table's, again, very jagged, possibly sticky. So there's a chance this holds still, and that means this one would also hold still, right? There's a couple of conclusions I want to draw about that fact. One, which of those 2 versions happens will affect what type of friction exists in this situation. If box 1 is held in place, not moving, and therefore nothing accelerates, what type of friction would be present? Very good. If box 2 does start sliding, say the tension of the rope is enough to pull it forwards and therefore to pull box 2 downwards, what type of friction would we have then? Kinetic. Very good. So, 1, which chain of events takes place affects which of those 2 friction numbers we need to use. The other thing I want to mention is that either version of events, the acceleration of the 2 objects is synchronized. These 2 things are tied together. So if one of them accelerates, the other has to come with it at the same rate. If 2 things are tied together, they're going to share an acceleration. If one of them is being pulled forwards, the other's getting dragged along behind it. You and all your friends are together in a car and the car starts accelerating, you are accelerating at the same rate along with it, right? So, one added thing that we can say about this whole ordeal, whatever A1 is, the acceleration of box 1, A2 is going to match it. If the system doesn't move, they're both going to have an acceleration of 0. And the friction type present would be static. If they do start moving, object 2 is going to get pulled down, object 1 is going to get pulled forwards. Different axes, but the same magnitude of acceleration because they're tied together. The string's going to travel along with them. If that happens, they'll be accelerating at a non-zero rate, but it'll be the same non-zero rate. And in that scenario, kinetic friction takes over. So either version of events, we have to pick the right version of friction, and the two A's will match, no matter what. We're gonna take advantage of that fact. That's another quirk of pulley questions. The acceleration on both sides tends to match. Now, the first actual question here. Assuming the system will begin sliding, which type of friction will be present? Kinetic. So, the premise we're going to operate from here is that the table is too slick to hold box 1 in place. It's going to start sliding. The two objects will have a shared non-zero acceleration, and kinetic friction is going to be the one that we look at. So mu s, just going to ignore it. It's gone. It's not going to matter here. That's why you read the question. This number is a distraction. Whoever wrote this textbook is trying to trick you. Don't let them win. Things are going to slide. We're going to use mu k to find force of friction, k. And now, with that assumption made, we will continue on to look at the rest of the scenario. But before we proceed, I'll go ahead and do that. So, questions before we move on? Now, the main things we're being asked here are how fast is the system going to accelerate, and what is the tension in this string? That's two things we're looking for. And to kind of give the game away, I'm listing both at once because we're going to end up in a two equations, two unknowns scenario. So we'll find both of them pretty much at the same time. And we're going to do that by analyzing all the forces present on each object, look at how they all add together, and see how they all contribute to the overall acceleration of the system. So again, we're kind of combining all of Newton's laws and all the forces we've looked at together into one big ordeal here today. So first, before we do any math, we need to look at this scenario and identify all the forces that are present here. So we're going to take our picture here and turn it into a free body diagram by drawing arrows all over it. I already put tension up here to illustrate how the pulley works. So tension's acting on both of them. That's one force out of the way. How many other forces are acting on box 2? Gravity. It's not touching a surface, so there's no friction and there's no normal force. The only other force here would just be its own weight of 50 newtons. I'm just going to call that Fg2, but it's equal to 50. And those are the only two present on this second box. I started with the second one because there's only 2 arrows. Now, the other box is going to have a few more arrows. Again, we've already got the tension worked out. But what other forces must be present as it slides across the table? You guys are making good points. Just a little louder, please. Friction, very good. What direction is box 1 going to move in? Rightward. And that means automatically friction's going to point in the opposing direction of leftward. So when I add a friction arrow here, if the motion points that way, friction points this way. By definition of friction, it opposes the motion. If the motion is to the right, friction will be to the left. All right, what other forces are present? You were muttering very correct things. I just need to hear them louder. Gravity and normal force. We already know what the box weighs, so that's Fg1 equal to 100. And then also, the table must exert some normal force upwards, or else the box will just fall through the table. And those are the 4 forces present on box 1. So at this point, we've now identified all the forces, and And we need to see how they're all interacting to create the overall reality of the scenario. We need to see how they all add up and contribute to the net acceleration of the system. Now to do that, again, the goal is to add all the forces together and see how they cause net acceleration. We're going to look at Newton's second law and use it to add the force vectors together for each object separately. Since box 2 has fewer forces, I'm going to do box 2 first. So I'm going to write that out as net force 2, just to be specific. So the net force acting on box 2. Newton's second law tells us that net force equals mass times acceleration. Now, I don't know that box's acceleration yet, but if we're operating under the assumption that this whole system is going to start sliding, there must be some acceleration. And we've already determined that the two boxes will accelerate together at the same rate. So, whatever the value of net force is on box 2, it's going to add up to equal to mass 2 times the net acceleration of the system. So whatever net force is, it will be equal to box 2's mass times its resulting acceleration. And by definition of net force, that net force is comprised of the sum of all the forces acting on box 2. We've already listed all 2 of those forces, and conveniently they're both in the y-axis, so we don't have to do a split axis thing for box 2. As far as box 2 is concerned, there's only 2 things contributing to this net force: tension up and its own weight down. So again, the definition of net force is the sum of all the forces acting on it. Just take them all and add them together. And the other definition of net force is that it will cause the acceleration of box 2's mass. So these 2 things add up to ma. And as such, we have now analyzed all the forces present on box 2 and how they create its net acceleration. So this is vector addition. It's just vector addition that doesn't add up to 0. How do you guys feel so far? Okay. Now this one equation has both of the things we want in it. We want acceleration, we want tension, and we have those present here. We also know the weight of box 2, so we can eventually just plug -50 in for that. We don't have mass for box 2, but we'll get to that. We can quickly find that number when we need it. So this one equation has the same 2 things in it that we want, but the fact that they're both there and both unknowns means we cannot find out either of them yet. Again, we're going to build another 2 equations, 2 unknowns type of scenario. But that's all the information we can glean right this second. So now we're going to move on. We're going to look at box 1 in addition now. Feel good? Any issues thus far? All right. We're going to do the same thing to box 1. The only problem is box 1 has 4 forces pointing across 2 different axes. So we're going to do the same thing for box 1. We just need to do it once in the x and once in the y. I'm going to start with the x because it's the most immediately relevant to what we're trying to do here. So I'm going to write that out as net force on box 1, x-axis. It kind of looks like fix, so I'm making clear that that's a 1, not an I. So net force, box 1, x-axis. Looking at our picture here, the 2 of these forces that point in the x-axis are tension forward and friction backward. And those must add up to box 1's mass times its acceleration, because box 1 will accelerate in the x-axis. So box 2 accelerates in the y, box 1 accelerates in the x, again because the rope is changing the pulley is changing the axis of tension. From box 1 perspective, its mass times the resulting acceleration will equal the rope's tension minus, just because they oppose each other. Oh, I'll make it plus, we'll do the minus later. The force of kinetic friction trying to slow it down. Those two things add up, they oppose each other, but they add up to mass times acceleration. So that is box 1's x-axis in the line. And that axis has the same two unknowns in it, both acceleration and tension. So we're getting to that point of two equations, two unknowns. We're going to be able to combine these two equations here to get what we want. The only reason we can't immediately proceed with that is we don't have a number for force of kinetic friction yet, and we also need to work backwards and find the mass of each object as well. Now, how do we find the force of friction on an object?
Force times the coefficient of friction.
Yep, got it right here. Force of friction equals normal force times mu. We know the coefficient of kinetic friction. We've already established that kinetic friction is the type we like here, so I'm going to add the two k's there. We know the coefficient of kinetic friction between box 1 and the table, but to get force of friction kinetic, we also have to make a quick assumption about what the normal force acting on box 1 is. And I'm sure you can quickly jump to that assumption in your head, but I'm just going to show mathematically where it comes from. By examining the y-axis forces acting on box 1. So same process, but now it's net force box 1 y-axis. Is box 1 accelerating in the y-axis? No. So whereas box 2y and box 1x are both mass times acceleration, here box 1's y-axis acceleration is 0. So net force on box 1 is 0. I guess you could also say that the x-axis acceleration of box 2 is 0. So they have zeros somewhere. Box 1's y-axis net force will be 0. Therefore, the two y-axis forces on box 1, normal force up and its own weight down, must add up to 0. Therefore, if box 1 weighs 100 newtons, the normal force acting on box 1 must also be 100 newtons. Again, some of you probably assumed that yourselves. I'm just showing the math of where we get that assumption. It's always good to show your steps, especially if you're the teacher. Now with that done, we can figure out force of friction, which we can then plug into our previous equation. Any questions on arriving at that conclusion before we use it over here? All right. So, absolute value of force of friction equals absolute value of 100 times point. I like putting zeros in front of my points. 0.32. Therefore, the magnitude of the force of friction should be 32 newtons. I'm keeping the absolute value brackets in because this formula technically cannot by itself tell you the direction that friction points, since again it bridges axes and one axis doesn't really care about plus or minus in the other. That's why I put the absolute values here. So I kept an absolute value on the answer because the formula alone does not tell you, cannot tell you, if that friction points forward or backward. So we have to do that ourselves slightly. We know it's 32. 100 times 0.32 is 32 newtons. We just have to be careful about how we use the number. So I'm going to take that number, plug it into our other formula. We don't have M1 yet. We'll get it briefly. So we'll leave it blank for now. M1 times A equals our unknown tension minus 32. And we do that because it needs to oppose the tension. This formula can't give you that negative. We have to set that up ourselves by observing tension and friction must point in opposite directions. You could make tension negative, in which case the 32 would be positive, but you gotta put a negative somewhere. Does that feel okay? Does that track so far? Questions, concerns? All right. So that's force of friction figured out. Now we also need the mass, both masses of our two objects. This question does something slightly different, and it started with the weight of each one. So now you have to work backwards to find the mass. How do you think we should do that?
Force of gravity.
Yeah, we know the formula for force of gravity. We have the weight, we want the mass, and G is always negative 9.8. So rather than using this to find force of gravity from mass, we can use force of gravity to find mass. So for box 1, its weight of 100 newtons down is going to equal its mass times an acceleration of negative 9.8 down. Therefore, M1 must equal negative 100 over negative 9.8. About how much mass does that generate? Very good. Note that it is positive because the negatives will cancel out. Negative mass doesn't really make any sense, so that's a good thing. And that would be the mass of box 1. Note again, we were given the weight of the box because this number has a newtons attached to it, not kilograms. 100 newtons means weight, so we used it to find mass in kilograms. And that is the number that we will now plug in for M1. So 10.2. And so, our x-axis equation for box 1 is now simplified to where A and T are the only two unknowns left. And now we need to do the same thing to this equation so that we can combine them and find those two things. Any issues thus far? All right. Now, our first formula, similarly, we still need the mass of box 2. We want the tension. We already know box 2's weight, which is good. Now, tension and weight oppose each other, so they do need opposite signs still. Weight pulls down, and tension's pulling up, so I'm just gonna make T positive and gravity negative. And we're also going to need I wasn't even losing my train of thought. That was losing the ability to speak for a second there. We need M1. We need M2. We need M2, sorry. But we can do the same trick we did to find M1. The only difference being box 2 weighs half as much, so it should have about half as much mass, right? So M2 should be negative 50 over negative 9.8. And if we just cut the other mass in half, that should be about 5.1. Correct? Anyone argue with that? All right. Again, the negatives cancel, which is good, because negative mass implies that well, mass isn't a vector, so it implies that you either have less mass or you have anti-mass. One would blow up, so let's hope it's not that. Sorry for that tangent. Our formulas are almost complete and almost ready to go. There's one small hiccup that I need to address. One teeny tiny hiccup. These two objects are going to accelerate at the same rate, or rather, their accelerations will have the same magnitude. But because of the pulley, they don't quite have the same direction. Note that box 1 is being pulled forwards, which we treat traditionally as being positive, whereas box 2 is going to get pulled down, which is traditionally a negative direction. Their accelerations will be the same number, but technically speaking, they would have different signs for that reason. Same number, but opposite signs because of mostly pulley weirdness. We can use this and put the same A in those two places. We've determined that their separate accelerations would have the same magnitude. And so rather than this being A1 and A2, we can make it the same A. One problem is with that, one of those A's should be a positive number and the other should be negative the way that we've done this so far. We can account for that. We just have to add the negative ourselves. Kind of like how we manually had to add the negative on the force of friction. Because our equations, as useful as they are dumb. These are equations. They are not human brains. They do not have this context. We have to add that context manually. So that negative is meant to represent that box 2 accelerates down the negative direction, and box 1 accelerates forward a positive direction. And if we don't put that negative there, our math won't work out quite right. Because the formula needs to know the tension is a value such that this object moves down. The tension is weaker than the gravity. If we don't put that negative there, things are going to break, and your calculator might yell at you. Or actually, the main problem is just that the answer wouldn't make any sense. So it's a weird quirk, and that's why it's very important to track direction for vectors in everything you do. You guys feel all right? Any issues there? It's okay if it's weird. Physics is weird. Again, keep track of direction for every single vector. And after all of that, we have arrived at two equations, two unknowns. We have two different functions that both have tension and acceleration in them. So at this point, it's kind of up to personal preference how you choose to combine them and get the two final numbers there. We could solve one of them for t, plug it into the other to find a. We could solve one of them for a, plug it into the other and find t. There's more than one correct way to proceed with the math at this point. I would like to demonstrate a slightly modified tactic, because I think that the way that these are written behooves the way that I'm about to do it. You do not have to agree with me. There is multiple ways you could do this correctly. I just want to demonstrate an option. Rather than solve one of these for something and plugging it wholesale into the other, I'm actually going to rearrange both of these for t real quick, just to kind of demonstrate how that works. I'm going to take both of these and turn them into t equals blank. Up here, that's going to look like sending 50 over to the other side. So t is going to equal negative 5.1a plus 50. And down here, I'm going to send 32 to the other side, and that's going to give us t equals positive 10.2a plus 32. So now we've got two different functions, t equals blank. And they both have the same a within them. And so that's two different functions that equal each other using various properties of math. If both of those things equal t, then they must both equal each other, correct? I'm going to write out an in-between step here. Negative 5.1a plus 50 equals t, and then separately, t equals 10.2a plus 32. If all three of these parts equal each other, then we can just choose to cut out the middle part, right? And set the two other sides equal to one another. And then, I'll put the a out. We've eliminated t. Now, whether you think that this is less steps than any of the other methods, totally up to you. I just kind of like how this looks. It gels good with my brain. Not the only tactic, but it's one that I like for this scenario. Any issues arriving at this point? At this point, the goal is now to get all the A's together on one side and all the not A's together on the other. So I'm going to drag the 32 over here, 50 minus 32, and I'll just write the whole thing out. It's going to give 50 minus 32, and as we send the other A term over to the right, that would be 10.2A plus 5.1A. This is really why we needed to make that A negative over there, so it became positive over here, so that they add together rather than subtract from each other. Trust me, math wouldn't work out quite right if we hadn't done that. Now, both of these don't have A, both of these have A, so they do add up normally on each side. That should be 18 equals 15.3A. Any issues seeing how that works? All right, and then lastly, A should equal 18 over 15.3, which my memory serves is about 1.18. Does anyone disagree? What would the unit on that answer be? Meters per second squared, very good. Acceleration is meters per second squared. So that is the rate that this whole system begins accelerating at. How do you guys feel? It's okay if you don't know how you feel. Emotions are weird. A quick conclusion I'd like to point out about that number. That is the rate that box 1 is going to get pulled forwards, and also the rate that box 2 is going to get pulled down. Same magnitude, but different directions for each. And an interesting thing about how that works for box 2 specifically is that is an acceleration downwards, and falling is also an acceleration downwards, but falling is negative 9.8 meters per second squared downwards. That is like an eighth or a seventh of that. No, a ninth. It's a ninth of that. Yes?
So, for the answer, would you put 1.18, like one positive or 1 negative?
If you wanted to be specific, A1 would be positive. Here, I'll write it out. A1 is 1.18 meters per second squared forwards. A2 is negative 1.18 meters per second squared, referring to downwards. Same number, but because of the axis swap, a different direction for each.
So will we have to show that on like the test, or we could just put that number in?
It depends on exactly what the question, it depends on how the question is worded. You know what, let me actually slightly tweak the text of the question to match what I'm about to say, to kind of match how I set that up. Okay. So, I did change the wording slightly. What I've got here now is, what is the magnitude of the system's acceleration? And magnitude is the fancy way of saying, what is the number? And for both objects, and also the string that they're attached to, the number is 1.18. It just represents the speed, the rate at which it is happening, regardless of direction. And so, if it asks for a magnitude, it is just the number like we did over here. If it asks, magnitude and direction, and wants you to list it separately, like if it says magnitude and direction for each one, you would list them separately. So, depends on the wording of the question. Did I address your concern? Okay. So, I'd like to point out, they're both going to accelerate at this rate. Box 1 forward, box 2 down. If box 2 was just falling, unassisted, it would accelerate down at negative 9.8, correct? Here, T1 is pulling up on it, slowing that process down. It's still accelerating, just not nearly as fast. So this is kind of consistent with what we would expect, right? It is descending, but not nearly as fast as if we just cut the string. The tension is slowing it down. Does that make sense? All right, so this number is great. It makes total sense. I like to point out how the numbers apply to reality to build your frame of reference. And now that we have that number, a number for A, we can take it over to either of these things to find a value for tension. I'm going to use box 1 for that. T equals 10.2 times 1.18 plus 32. And if my memory serves, please let me know if your calculator says otherwise. That would be about 44 newtons. And that is 44 newtons acting on both objects in different directions. And to kind of point out how that number makes sense again, to help build your frame of reference so that these aren't just meaningless numbers. That 44 is pointing up. It's acting upward on box 2 and acting rightward on box 1. From box 1's perspective, 44 newtons forward is bigger than the 32 newtons of friction backward, correct? That means that the tension is stronger than the friction, and that's why box 1 is being pulled forwards. On the opposite hand, from box 2's perspective, it's being pulled down with 50 newtons of its own weight, and the tension upwards is only 44. That means that box 2's weight is bigger than tension, and that's why it's being pulled down. So kind of like that pulley I drew earlier, it's the same tension inward on both sides, but the two forces opposing the rope are different from either number. And in fact, one end is weaker than the other, which informs the direction the whole system moves. Overall, this end is being pulled down with 50, and this end is being pulled back with 32, so the whole system proceeds down and forwards. I could change this whole question to remove the pulley and just make it a back and forth tug of war match. Team 1 pulling with 50, team 2 pulling with 32, and you get the same result. How you guys feel? It's okay if you don't know how you feel, because this was a long example and also a weird one. It was weird. And we're pretty much at the end of the lecture, so we're just gonna, we are at the end of the lecture, so we're gonna cut it off here. Again, frame of reference. This was like on your homeworks and also on tests. There's usually like one question that's kind of designed to be a doozy. This is that. This is everything combined together at once. Okay, this needs time to sink in. Again, this was the weird one. This was literally everything from the past week lumped together all at once. Yes?
So the tensions are gonna be the same?
Yeah,
Okay.
that one T number, 44, pulls rightward here and upward here on both.
And then, like, you could plug it back into the other T, like the negative 5.1A plus 50 if you wanted to, and you'd still get it.
Yep, if you plugged 1.18 there, you get the same T. Likewise, if you take this T and plug it in here, you'll get an A back out of 1.18.
Okay.
Any other questions for right now? All right. Do be looking over your homework. Let me know if you need anything. And if you have any questions or issues about this that formulate at any point over the next couple of days, let me know. We'll start on Friday with some review before moving on to new stuff. Have a great day.
I made these equations for I did them point one difference between the two. That
I would just chalk that up to rounding and consistency. That's fine. Like if you carried sig figs all the way through, it should have worked out. So I don't